Good afternoon. Thank you for joining. Yes, there is maybe a question. I don't know. So let me. Okay, thank you for joining, and I wait just 1 minute more to be sure that all the people can be with us. So let's start. First of all, I would like to remember you that this webinar is recorded, and that we have the possibility to take time for question only at the end of the presentation, just to make easier the presentation of the contents, and then to have the enough space for an eventual discussion. Thanks again for coming. Good afternoon. My name is Gianpietro Pagliarini. I'm RIPAC Vice President dedicated to operation and research and development activities. And RIPAC is a manufacturing company located in the north of Italy, and is part of Promac Group. Is a big group of company specialized in the manufacturing of different type of machinery for food and beverage. And in particular, RIPAC is manufacturing different type of packaging machineries and solutions in automation. Today, there are other persons helping me to present the contents of Zero Swarm project, and in particular, I'm speaking about Mario and Domenico from Research Wings, and Giovanni from TTS.
Hello, everyone.
Hello.
So, Zero Swarm, as you know, is an European project, and RIPAC take part in Zero Swarm as an industrial partner. In particular, for the development on some industrial technologies, but also for, and especially, for the validation of the technology we are providing, and also the technology that other partners provide during the project. RIPAC trial, identified as a South Node 1 and 2, refers to a specific industrial scenario, in particular, the full automatic packaging lines for ready meals product. And in these two videos, I'm sorry for the volume. Okay, in these two videos, I would like to show a typical production plant of RIPAC customers, specialized in the ready meals for airplane or hospitals catering. This packaging line is composed by different devices, mainly by a dinester unit used to unstack a pile of empty trays, and this type of empty trays can move along an in-feed chain conveyor for transport, for the transport of the containers. There are dosing stations for liquids or solid products, usually managed manually with different people to dose and fill the trays, or automatically. There is a tray sealer machine to pack the product into trays in standard atmosphere in case the product must be consumed in a short time, or in modified atmosphere packaging in case the product can be consumed after a long time. Then normally there is an outfit belt conveyor connected with maybe inline check waiter devices or a quality control unit. At the end of the line, normally there are stations dedicated to the automatic handling of critical food products or critical trays, maybe in case of palletizing and so on. If we consider an industrial production plant, all data related to the production and specifically to the machine are collected usually in an advanced platform, in this case compliant with Industry 4.0 principle, and as well integrated with the factory management system. It was impossible for us in Zero Swarm to reproduce a so big and complicated packaging line as you can see on the left side of the picture. So that we decided to create a compact version of this packaging line, giving the possibility, in any case, to study and to take in charge all the troubles of a more complicated packaging line. But one by one, we have reproduced the usual components, the usual units of a typical industrial packaging line. So we have the nest, in this case, a standalone solution. We have the packaging machine, in this case, a tray sealer. And we have a collaborative robot to reproduce the automatic handling of the food product. In addition, we have a station at the end of the line for the quality control. And in Zero Swarm, we have introduced also the concept of the logistic based on AMR devices. The main purpose of this project is to realize this kind of packaging line controlled thanks to an advanced hardware and software architecture based on the standard 61499 and the hardware able to support this kind of standard from in terms of programming. The second main purpose is to use an advanced system to manage the AMR in the same network where the machine works. So according to Zero Swarm specification part of the Work Package 2, with reference to repack trial, has been studied or has been defined a specific hardware and software architecture designed to empower the use and the advantages of automation solution, as already I anticipate, based on the standard 61499. In particular, we have three different layers. One layer related to the devices cooperating in the management of the different activities related to the packaging process. We have a layer related to the solution, the control solution to control the single devices, and the higher level, based on all data management and relative protocol of communication. And I would like to underline and mention, for example, the use of nano PLC devices, in our case named ice blocks, as an example, used for an example of distribution control, one of the principles of the standard. At the meantime, we are using a M262 Schneider Electric PLC as an example of a PLC for industrial application based on software developed according to the principle of the standard 61499. The use of advanced AI algorithm for an example of complex logistic into the packaging production line. And we have an AMR just to emulate a fleet management. In our case, the AMR is Omron branded, fleet management according to the production scheduling and the continuous rescheduling of the priority of the mission and the task. And this kind of a priority can be related also to eventual necessity in terms of extraordinary maintenance. Finally, we have the edge virtualization on a Schneider Electric edge platform of the algorithm, and the Renext platform, and a platform industrial 4.0 compliant, including the cloud virtual commissioning. We have also used communication protocol communication as Wi-Fi and the structure to manage also 5G communication in a 5G network, and the OPC-UA communication for the data management and collection in terms of at automation level. This is an overview of the hardware we are using, and I have already explained, and also an overview of the different protocols according to the type of communication we have developed and validate. Now, let me introduce Mario and Domenico, part of Research Wings team, technology provider in Zero Swarm dedicated to AI algorithm topics. Thank you, Mario and Domenico.
Thank you. Thank you, Gianpietro. Good afternoon, all. Here we are, Mario and Domenico from University of Salerno. We are researcher, and we are helping Research Wings for the project Zero Swarm. Research Wings is a technology-focused organization that contributes to advancing intelligent manufacturing solution, particularly with the Industry 4.0 landscape, specializing in areas like edge-to-cloud computing, machine learning, and optimization. Today, we will discuss the role of autonomous mobile robots, or AMR, in enhancing efficiency within manufacturing environments. Our focus is on managing fleets of AMRs in packaging line. In fact, through Zero Swarm scheduling system, we can optimize robot task assignment in real time, improving productivity. AMR could be equipped with essential sensors like cameras, radars, and sometimes robotic arms. These sensors allow the robots to navigate, recognize objects, and handle materials. With onboard computing power, they can process this data in real time, make autonomous decisions, and execute tasks within the production environment. Our AMR fleet plays a crucial role in production by transporting materials, like ingredients and packaging, to wherever they are needed along a predefined layout. Each AMR follows its designed route, allowing multiple robots to work together seamlessly within the production environment. At Research Wings, we developed and tested a prototype to demonstrate our framework for AMR fleet management. This framework operates across the edge cloud continuum, enables accurate battery prediction and dynamic job scheduling. In fact, we developed an algorithm for job scheduling using optimization and machine learning. Then we will see how with Domenico. For the moment, just keep in mind we have two modules working together for the same goal, the scheduling of the jobs. Key technologies used include Django for the framework, Keras for machine learning battery study prediction, Google OR tools for scheduling tasks, and Postgres as the database. The result is a fully operational prediction and scheduling module integrating in the cloud-to-edge architecture successfully deployed at the Repax gateway node. Our system prototype is structured across three sections, edge, gateway, and cloud, each playing a distinct role. On the edge, we have modules for data acquisition from sensors, battery status prediction, and anomaly messaging via MQTT. The gateway translates OPC-UA data, making it interpretable for cloud application. Finally, the cloud side uses Django microservices to manage mission scheduling, bacteria prediction, and MQTT messaging, supported by Postgres database. Here we have a video. Can we start it, Gianpietro? Thank you.
Yes.
Okay, perfect. In this video, we can appreciate the prototype we developed with this graphical interface. Specifically, we can manage the fleets. For example, we can add a new fleet, adding a new AMR and assign it to a fleet, or reassign it to another fleet. We can see it in the video. I go faster. This is an updating of a fleet. Here is list of resources belonging to a fleet and the possibility to assign or reassign the resource to a specific fleet. Then we can go faster.
Okay.
On the details of the single AMR. Here we are displaying data coming in real time from the device. Specifically here from the AMR with ID 2. In this section, we have also a historical data section and the details of the battery status using the predictor for the future values and the list of the job we assigned to the AMR. So here we can see all this data. This one is for the data coming in real time from the AMR. Then we have the battery prediction section. In blue, the data coming from the AMR, and in red, the predicted one. Here is the section with the job assignment, list of job in diverse status. And then we have the historical data collected by the system for this resource. Okay, we can go on. And we can focus on the prediction service module, which uses a deep learning model, specifically a feed-forward network with a sliding window, to predict battery levels based on historical data. This model is always active and runs on a OPC-UA server, where it continuously retrieves battery percentage for each resource. For each device, a dedicated predictor is created, updating the OPC-UA object in real time with the latest battery prediction, ensuring accurate and timely monitoring. Here we have the performance results of different machine learning models we tested for battery prediction accuracy. We compared feed-forward networks, gated recurrent units, and long short-term memory networks at various input lengths. Based on the mean square error highlighted here in red, the LSTM model with an input lag of 100 showed the best performance with an error of 0.4, indicating its effectiveness in handling sequential battery data for more accurate prediction. But Although the LSTM with this length of 100 had the lowest error, we opted for the feed-forward model. This choice was due to the robustness against the overfitting, given that our model was trained on a laboratory-generated dataset. Accepting a slighter error margin, the feed-forward network offers a greater generalization. This diagram, whereas, illustrates the architecture of our prediction service module. Each resource identified by a unique ID reports its battery percentage to the module via OPCUA. Within this module, individual predictors are instantiated for each resource, analyzing battery data and generating prediction. These predictions are stored and updated in OPCUA object, which can be accessed in real time. But in addition, we have a RESTful API endpoint to retrieve prediction for any specific resource ID, enabling seamless interaction with external system and application. In the next two slides, and specifically in this one, we have an example of OPCUA object structure for a specific resource, identified here as prediction 1. Key fields include the last update timestamp, lookback, which refers to the range of historical data used, predicted values containing the battery prediction, and queue, which organizes incoming data. The ready field indicates the prediction status, showing wherever it's up to date and available for external access. We provide two methods for accessing the battery prediction trend for a specific resource. The first method is through direct access to the OPCUA object for the resource, and the second is through a RESTful API predict endpoint. This slide provides an example of the RESTful API response for the prediction service with a specific resource ID 1. In the response, we see the prediction values representing upcoming battery levels and previous values showing recent battery history. In this slide, we demonstrate an error response from the module when the prediction data is not currently available, often due to insufficient values of generating prediction. In the next slide here, we demonstrate a successful REST API response for the prediction service module. Here, we call predict6 to retrieve the 6 predicted value for the resource with ID 1. Furthermore, using the REST API predict with the option status, we can retrieve key information about the prediction availability and readiness. The response includes ready, which tells us if the prediction for the specified resource is available, actual queue size indicating the number of values currently in the prediction queue, and lookback representing the number of required values to generate a prediction. Let's see some examples. In this slide, the response with ready false indicates that the prediction is not currently available. It also shows that an actual queue size of 9, meaning none values are in the prediction queue, while lookback requires 25 values to generate a prediction. In this slide, we again use the RESTful API, but with the status true, meaning that the prediction is available. Both actual queue size and lookback are 25, indicating that the queue contains the required number of values, so generate the prediction. So this is how the prediction works, how this module works. And with Domenico, let's see how the schedule can use this information. Domenico, the shop is yours.
Okay, thank you, Mario.
So So a fundamental step before even being able to implement the scheduling algorithm was to define a representation of the shop floor. And so we used a graph representation enriched with metadata that we called layout. So for example, in this figure, we can see the shop floor divided into different areas of interest, which are, for example, the area where the charging stations are located. Then we have the area where the ingredients are stored and the area where we find the packaging material. And these two last areas represent the picking point of the AMR. And then we have a packaging line that represents the drop-off points for the AMR. So this area can be represented using a graph composed of arcs and nodes labeled in a specific way so that we can recognize the specific points. So we store the layout into a database and we distinguish between network intersection that represent the nodes of the graph, so that represents the points where we can ask an AMR to go. And they can have also different type. That this type are used, for example, to recognize a specific depot or just a passing through node. Then we have network links that represent the arcs of the graph, so represent the direction that the AMR can take for move from one node to another node. And also these can have several types that can represent, for example, only a specific type of AMR can pass through specific links or other information. So we have defined a layout module that can be accessed using a REST API in order to modify and access the layout. After that, we define another module that is the scheduler module that wrap the scheduler algorithm. Also, this module can be invoked using a REST API in order to ask to schedule a specific set of jobs on a specific set of AMR on a specific layout, returning in output so the scheduling of the jobs to the AMR, so the assignment of the jobs to the AMR, and so defining also the order in which an AMR has to address a specific jobs. So here we have a representation of a use case example. We have first a representation of the layout in which we have inserted an area where the AMR are parked, and this area represents also the starting point for each AMR. Then we have a dedicated area for the AMR charging, where the AMRs can go to self-recharge when the battery has dropped below a certain threshold. After we have three hypothetical areas inserted, for example, but they can be seen as three distinct warehouses that are, for example, refrigerated room, a fresh food storage, a packaging storage, and then we have two packaging lines. On the right, instead, we have the scheduler output, and on the x-axis, we have the time instance, and on the y-axis, we have the AMR. The blocks represent the jobs that must be executed in a specific order, so in the order in which we can see now on the picture by each specific AMR, and the size of a blocks indicate the number of time instance required to execute that specific job. Below, instead, we report some information for each AMR, which are the percentage of charge and the weight carried out in that specific model. We can notice that all the AMR are at 100% of their battery and only AMR4 is at 30%. So by indicating the AMR with colors and scanning the chart from left to right, we can see how the AMR moves on the layout. We can notice that at first time instant, AMR1 has completed this first job, which consisted on carry out a picking operation in the refrigerated room. And after this operation, his battery went from 100% to 80%. Of course, this is just an example because battery discharges much more slowly. At the end of the second time instant, we can notice that also AMR2 and AMR3 also finished their first job, which was for AMR2 consisted of a carry out a picking operation at fresh ingredient storage, while AMR3 a picking operation at the packaging storage. While AMR4, which was out of battery, reached the charging station. At next time instant, While the other AMR performs their jobs, AMR4 remains stationary and recharges itself. And the process continue basically in this way until we reach the last time instant. So, but how was our scheduling algorithm implemented? So in order to implement the scheduling, we defined a mathematical model and we solved it using a free solver from Google for mixed integer linear programming problems. We can notice that in the objective function, we minimize Emax multiplied by parameter alpha plus Cmax multiplied by parameter beta. In this case, Emax represents the energy consumption. That is, we try to carry out all the job wasting as little energy as possible, while Cmax represents the time needed to complete all the jobs. So, if beta is equal to 0, we minimize only the energy consumption. On the contrary, if alpha is equal to 0, we minimize only the time span, so the time required to perform all the jobs. So alpha and beta can assume a value between 0 and 1 in order to balance these two objectives. Obviously, the sum of alpha and beta has be equal to 1. This model also incorporates the use of lambda estimator, which integrates prediction from the machine learning model described by Mario before, in order to forecast the battery state of charge of a specific AMR. The introduction of this parameter means that the mathematical model takes into account the status of the AMI battery, so a job can require more or less time to be performed depending on which AMR it is performed by. So the results achieved show that this approach ensures that the tasks are dynamically assigned based on the battery condition, preventing downtime and saving battery. So in this slide, we report a table that is focusing mainly on the execution time required by the mathematical model. The first column describes a specific scenario. We have the number of AMR, the number of charging station, the number of job nodes that represent a node in which we can perform or a picking operation or a drop-off operation, the number of jobs, and other columns that are related to the solver. But if we focus on the time column, we can notice that the solver requires always less than 4 seconds. So it's very fast. On this other slide, instead, we report some experimental results of the mathematical model, including or excluding the lambda parameter, using a different combination of alpha and beta. So, as I said before, alpha determined the energy efficiency, while beta the time optimization. We evaluated these results in terms of number of charging operations performed. The more charging operation we do, faster the battery deteriorates, and in terms of time required to execute all the jobs. So for example, in the first scenario, where alpha is equal to 1 and beta equal to 0, meaning that we are trying only to optimize the energy consumption without caring about the time optimization, we can notice that if we exclude lambda, we execute many charging operation. Here I forgot to report the average values, but on average we pass from 18 number of charging operation to 12 number of charging operation including lambda, obviously increasing the time required to perform all the jobs. Instead, in the opposite scenario, which is the last, where alpha is equal to 0 and beta is equal to 1, nothing changes if we introduce the lambda coefficient, obviously because we are not optimizing the energy consumption. While in all the other scenario, even if we give a slowly priority to the energy efficiency and higher priority to the time optimization, the number of charging operation always decrease. So this was my last slide. So I give the floor to Gian Pietro.
Okay, thank you. So now I'm just checking if Giovanni from TTS is in the Teams. Maybe not. He could have some troubles, maybe. But anyway, so this is a slide dedicated to the activities developed by TTS team, and is dedicated to virtual commissioning topics. In particular, they have using a model of our DNester is a standalone unit to unstacked trays. They have reproduced this kind of a model, and they have integrated their environment for virtual commissioning in the architecture we have developed. So in this case, we are able not only to simulate parts of the functioning of this unit, but also to validate in real time, or anyway, in the soft VLC, we are able to validate also the control solution we have developed from our side. So as RIPAC is. So now, in the last months of the project, we are focused on the validation of all these technologies and solutions developed in a previous period. And we have created in our factory a dedicated area representing different picking and placing points reached by the AMR according to the assigned task. So this is, let me say, an example of layout, just simplified for validating the concept. And in this case, we, according to the production orders, are scheduled into or thanks to Renex platform. It's possible to create a list of the mission for the AMR. And associated to this kind of list, we have a single task that the AMR will execute. In particular, the picking of maybe empty trays or film for the packaging for the top lid. We have also the picking of the food products. And in this case, we have a different location where to pick the products. Here, we are showing the concept that the AMR moves in front to the collaborative robot. This activity in terms of loading or reloading of the food product is considered manual. But in case of a more sophisticated architecture, the cooperation between the cooperative robot and the AMR can be realized in automatic way. So we have defined three main validation cases of a typical daily production into a packaging plant of ready meals. The first one is related to the first setup of the production line. And start from the setup of the machine, the device is cooperating in the production flow, including the line reconfiguration. In particular, to configure the line and to prepare the line, it's necessary that a specific production order is executed according to a recipe that is fixed into the HMI of the machine. This recipe is fixed and shared with the Renex platform, where we have the list of the packaging material and the ingredients will be necessary for that batch of production. And thanks to Renex platform, we share the information with the AI algorithm. The AI algorithm schedule the AMR task for picking and places of packaging material and ingredients, and the AMR interact also with the operator for the loading or or the recharging of the products according to the flow of the production. This is the first scenario. The second scenario consider the possibility that a reloading of the food product is required according to the consume of the packaging material or the food product, so that the AMR return to the base or go in a recharging, and when needed, according to the scheduling and rescheduling of the activities, moves to reload these components. The third scenario is related to extraordinary case of maintenance. Considering that Renext monitor continuously the status of the machine in production, monitor also the alarm condition. And in case a certain condition of alarm, we request an operation of the technician for doing maintenance, the AMR receive a task from Renext just to go for picking tools necessary for the operators. When the operator, the technician in this case, has completed the task, the AMR return the tools in the stock. This is an example of the interface of Renext platform, and in particular, another topic of the project is related to the use of an architecture based on Schneider Electric edge device, where Renext has been installed. Has been installed also the AI algorithm and the virtual commissioning part. There is an algorithm entitled to auto-recognize the presence of the AMR devices, just to combine a fleet of AMR according to the necessity, and the other algorithms are installed just to optimize and maximize the efficiency of the production according to the presentation that Research Wings has already done. Here you have the example of the part of the installation has been done. This is just a picture of the database, and this is a picture of the edge. This is another example of Renext pages, where you have constantly, according to the machine, we are monitoring the result of the production efficiency. We have the parts related to the production, the status of the alarm, the status of the warnings, because separated by the alarm, the cleaning, the maintenance, and so on. According to the list of the production order, we have also the possibility to fix the mission and the task as already explained. In conclusion, this is the roadmap of last validation step. And we are, for sure, everybody confident to finalize the project, reaching the expected zero storm result, and we count to that we are in the status that all technologies has already been integrated and pre-validated by the single partner. Now we are finalize the complete integration of these technologies, considering the architecture and the validation cases we have already presented. So thanks for your attention, and now before the conclusion, we remain at your disposal for any questions. So I invite you to participate and to share question if needed, maybe to be more clear or to complete the presentation.
There is one question in our chat.
Yes.
You could have a look.
So thank you for the presentation. Thanks to you. Did you think about more potential future use cases for this architecture in addition to battery life prediction or other aspects that could be optimized. So as an industrial partner, I answer you starting from my point of view, and then I leave Mario and Domenico to integrate. Yes, for sure. This is the first step from my side as an industrial partner interested to use logistic more advanced that actual know logistic application in our sector because in a different point of so in comparison with other sector in the packaging is not so easy to have this kind of solution, practically almost never known, to have this kind of solution in the real production line where you have people loading and managing products. For this reason, so we know that is not so easy because there are different difficulties. One of these is the optimization of the battery monitoring and recharging scheduling that we tried in Zero Swarm to define, and for sure we have the idea to implement deeply. And the second point is the real-time management of the task. Because in a sophisticated, in a very complicated production line, the rescheduling of the activities in combination with the kitchen and so on is really very hard. And for sure, the line we have defined in Zero Swarm, we think that is the right line, but we have to go more in the details in the sense I have explained. Mario and Domenico, I don't know if you want to add something from a technology point of view.
Yes, we in Research Wings have developed a simulator to test several use cases respect to the Zero Swarm goals. But we are now focusing on something more, extending them to test other use cases when the battery of the AMR is really deprecated. So we want to demonstrate that using our algorithm, both machine learning and optimization, we can reach a prediction or about the status of the created battery, anticipating a possible failure. So we can exclude that EMR from the scheduling and assign the jobs to the other EMR, saving times and of course the preventing downtime of the entire fleet.
So, for example, in terms of maintenance or prediction of a possible failure, we are already doing something about the packaging material, the packaging machinery, and the different devices compared to the production. So this module can be extended also to AMR and let me say, improved also with the use of AI algorithm. And the other point, also considering the possibility that one AMR can be not in a ready status or in other condition of work, we would like also to go deeply in the use of the virtual commissioning, because sometimes a part of the scheduling can be optimized, simulating or using different configuration and different number of fleets of AMR, and it could help the operator to, according to the usual production planning, can help the operator for understanding how many AMR are necessary for that factory. Other questions? Thank you. Nice presentation. Could you provide more details about the computation of the parameter lambda?
Okay, this parameter is calculated by a difference between the predicted values calculated by the prediction module and the linear battery consumption we defined in the scheduler. Domenico maybe can add something to the model we implemented in the scheduler model.
Yeah, so basically what we do is to take the model, the machine learning model that is trained on the data set that we generated. And what we do is to determine a specific lambda for each AMR. In this way, we can adjust the discharging function that in the mathematical model is is linear, so is determined by the distance that the AMR has to perform. And is determined also by the weight that the AMR has to carry it out. This lambda that is trained for a specific AMR. So we have also an index that is M. So we have lambda M, one for each AMR, that determine if this linear combination of parameter is trustful or not. Otherwise, we adjust it in order to make our jobs more energible.
Yes, in the end, this lambda parameter is a distance, an error between the nominal energy consumption and the real consumption made by the AMR.
I hope that we answered the question.
Thank you. Other questions? So we have still some minutes. So this is positive, Mario and Domenico. It means that we have been so clear that we don't need to. So now I ask you, Caterina, in case you have something to add related to Zero War, or maybe if can join also Puria or other partners of Zero Swarm in case they want to add something from a technology point of view.
Thank you very much. From my side, I want to, as always, encourage everyone to follow our page and to stay tuned for all the next webinars. And the next one is going to take place on 27th of November. So you all are warmly invited to it. And please never hesitate to engage with us for any question. That is from my side. Thank you.
Thank you, Caterina. Yes, for sure. It's important to remember that we are doing different activities to disseminate the contents and the activities we are doing. So for sure, it's important to stay tuned as and keep informed. Probably you have said, and I have missed that Did you use any messaging broker platform to collect the battery measurement? Mario and Domenico?
Yes, we have OPCWay object
Yes.
in our OPCWay server. We collected them in that way, and we expose also a RESTful API to have the possibility to access to these measurements from external application. We save them in a database. We expose them through API, and internally we share them on OPCWay server. The message broker we implemented through MQTT is used mainly for alarm messaging, and of course also for the auto recognition, auto registration of a new AMR.
Yes, it's important to say that at the base of this connection, there is a Renex platform, and we are sharing also through OPCWay communication data from the machine to Renex platform and collecting data for the other devices. We have a common database, and through the API, we communicate each other according to the necessity. Because through Renext, we show the monitoring of the status of the machine, but also the status of the AMR, including the task is processing and also the battery status. So it seems that we are perfect in time, because we have used the time available. If you have some last question, we are here available, or in any case, you have our contacts, and we can go on in the discussion or in the clarification, or just we can interact for thinking about new things that can be a contribution for us to develop something more, to implement something more or better, as we are doing. So let me say thank you, everybody, for the Mario and Domenico for the presentation, and all of you to spend time with us, and for the question also Antonio and Elvira.
Thank you for being here. Thank you, Gianpietro. Thank you all.
Thank you,
Thank
everyone.
you. Thank you all. Thank you. Bye. Have a nice day.
Bye.
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 Bye. Bye. Bye. Bye. Bye.